All right, this is the video for 4.2a, and we're talking about rational functions. So our objective is going to be find domain, the asymptotes, wholes, and lowest terms for rational functions. Okay, so first of all, the definition of a rational function is a function of the form p of x over q of x, where p and q are polynomial functions and q is not a zero polynomial. Okay, so that basically means that you have a polynomial over a polynomial. So it looks kind of like a fraction. Okay, so let's start out by graphing one of them just to see what it kind of looks like. Okay, so I'm going to graph 1 over x squared. You see how the bottom is a polynomial, the top is a polynomial, even though there's no x. It's a polynomial, it's just x to the 0 power, basically. So polynomial over polynomial, you have a rational function. So to graph that, I'm going to plot my x and y. So let's really explore this, okay? I want you guys to actually do this with me. When I pick 1 for x, I have 1 over 1 squared, right? What does that give you? It just gives you 1, right? 1 over 1 is 1. And when I pick 2 for x, 2 squared is 4, so I have 1 over 4. Okay, all this should make sense to you, and if it's too fast, just pause the video and kind of do the calculation on your own so you can see what's happening. Okay, if I put 10 for x, okay, 10 times 10 is 100, so it's 1 over 100. You see how y gets really, really small when I pick big values for x. Okay, and then if I pick something really big like 100, then it's 1 over 10,000. See, y gets so small, but it never really gets to 0. So y does not get to 0. And if I do the same thing for the negative for x on the other side of x, right, negatives, I get the same thing, because when I square it up, I get positive, so it's still a very small number, very small positive number, but it does not get to 0. Now, if I pick something really small for x, like 0.01, 0.01 squared is going to be 0.01, and 1 over 0.01 is 100, because 1 over something really small is something really big. So when x is really small, y gets really big. Okay, so the graph kind of end up looking like this. Okay, so you see how when x get really, really big or really, really negative big, like really far out, y gets really small, but it doesn't get to 0. Okay, the graph looks kind of like that, but it never really gets close enough to 0. It's just very, very small, but right above 0. And same thing here. If you pick something really small for x here, y gets so big, it goes up there, but it never really gets to 0 either. So these lines here, so there's a line that the graph does not cross, right? The graph gets toward this line, this vertical line here, but it doesn't really touch it, and that's called an asymptote. Okay, and the line going up here, that's your vertical asymptote. So x equals 0 is a vertical asymptote, and the line down here where the graph does not, like the graph approaches, that is called a horizontal asymptote, right? So y equals 0 is your horizontal asymptote. Okay, so you guys see that the asymptote, the vertical asymptote is really important here. So pay attention to the vertical asymptote for now. That's where the graph is discontinuous, right? So there's a cutoff here. The graph kind of does not touch each other. Okay, so we call that a discontinuity in your graph. Okay, so there are asymptote is not the only way that there's a discontinuity in the graph. The other thing is called holes. Okay, you can have holes in your graph, and I'll show you what I mean. Okay, so here the first graph, there is a vertical asymptote here, so the graph is discontinuous when x is 3. Okay, you see how it doesn't touch each other, so it's discontinuous at 3. And in this graph, it's discontinuous at -1 and at 2. See? In this one here, it's discontinuous at 2 because there's an asymptote here, and it's discontinuous here because there's a hole here. Okay, there's a hole at 2, so it's discontinuous at -2 because of an asymptote, and at +2 because of the hole. And one more is discontinuous at -4 because of the hole, and at -2 because of an asymptote. Okay, so let's look at the domain of these guys here. So rational functions, you can find domain by looking at the denominator, and the denominator cannot be 0. Okay, that's when there's a discontinuity on your graph. Just like when we talk about asymptotes and holes, that's because of the denominator cannot be 0. So here's a function, right? The first one we graphed, and the bottom cannot be 0, so my x squared cannot be equal to 0. And when I solve that, x can't be 0, and that gives me an asymptote at 0. Okay, so the domain is just x cannot be 0. Another example here, I have x minus 5 at the bottom. So I just look at the bottom, that cannot be equal to 0. I solve for that. X cannot be equal to 5. So if you graph that, there will be a discontinuity at 5. So my domain is x cannot be 5. Another one here, this one you have to factor it out, right? Just take that, not equal to 0. Factor it out. I have x minus 5, x plus 1 not equal to 0. So I solve that. X cannot be 5, x cannot be -1. So my domain is x not equal to 5, x not equal to -1. Okay, I try to do this pretty fast, but you guys should really kind of slow down, write it out, solve it out, pause the video so you can understand what's happening, right? You just watch this passively without taking notes, without thinking about it, you get really confused. Okay, so here, last one, x squared plus 9 at the bottom. So I put that equal to 0 again, and not equal to 0, and solve for that. Right, so x squared is not equal to -9, and I square root both sides. X is not equal to positive and negative 3i. If you have 3i, that means x cannot be some imaginary numbers, so x can be real. So your domain is all real numbers because it says x can't be imaginary, and in your graph, everything is real, so you don't worry about it. Okay, so all real numbers works. So the lowest terms, so these rational functions can be simplified, can be reduced into lowest terms. Okay, so we want to find the lowest terms, and this can help us find out whether we have asymptotes or holes. Okay, so let's do the lowest terms first. Here's a function, and what you do is I want to simplify, or I want to factor the top and factor the bottom. So factor out x on top, I have x times x minus 5. Factor the x at the bottom, x times x minus 4, and then you can cross out common factors, right? So I'm going to cross out the x with the x and have x minus 5 and x minus 4 at the bottom. That is my lowest term. Okay, now how do I know whether it's an asymptote or a hole? Okay, I look at the bottom. Here's the rule. Okay, this must be done before the crossing out. Be careful. Okay, you have to do this before crossing out. Okay, if the 0 in the denominator can be crossed out, it's a hole. If it cannot be crossed out, it's a vertical asymptote. So I look at x times x minus 4 equals 0. That's the bottom, right? And so I get x is equal to 0 or x equals to 4. Now, which one is a hole? Which one's an asymptote? The one that get crossed out, the x, that gives you 0, right? That is the hole. The one that cannot be crossed out, the x minus 4, that is the asymptote. So I have a hole at x equals 1 and a vertical asymptote at x equals 4. We'll do one more. Here's the function x squared minus 9 over blah, blah, blah. And of course, the first step, I want to factor the top and bottom and cancel things out. Right, so I get x plus 3 times x minus 3. And the bottom I have x minus 3, x plus 7. And we'll cross out the common factor there. And so my lowest term is going to be x plus 3 over x plus 7. And to see which one is the whole, which one is the asymptote, I look at the bottom, right? X minus 3, x plus 7 is equal to 0. So I get 3 and -7. Now, which one got crossed out? That one would be the whole, right? So the 3 is the whole, and the vertical asymptote is at -7.